We're going to talk about charge motion. And charge motion is response to an electric field. If there's an electric field, a charged particle will react to that. We know that electric field lines show the direction positive charges will experience a force. So the things that move the most are the loosely bound electrons in a material. If you think of this board, the protons are kind of what defines the material. The electrons can move a little bit. This is not a great example, doesn't have a lot of free electrons, but a metal piece does. It has electrons that are loosely bound to the atom, and they do most of the charge motion. So you almost never have protons doing the moving. So protons are not going to do this. They're locked into the material for the most part. An exception is when you have ions in a solution. We'll talk about that later. But most of the time we have electrons. Here's an electron. If I put it in an electric field like this, it's going to experience a force opposite the direction of the electric field. So that's what governs most of the charge motion that we're going to talk about. Now, another way of looking at it is that we understand if this is a big positive charge, an electron would be attracted. Or if this is a big negative charge set in space, these aren't moving, but the electron will be repelled. So that's an easier way of looking at it. Electrons are attracted to positive charges and repelled by negative charges. So the things that do most of the moving move in response to those. You can reason it this way, you can reason it this way. Both of those are reasonable ways to approach how charges will move. The first thing we're going to talk about is conduction. In conduction, is when two conductors touch, two or more, when there's a path of conduction, a path for where there's a conductor connecting things, or when two conductors touch, excuse me. So an example would be this. If I have a steel ball there and a steel ball there, and let's say this has a net positive charge. What does that mean? It has more protons than electrons. It has a ton of electrons, has a ton of protons, but some electrons have been removed at some point. That's the way you tend to get a positive charge on a conductive ball. And again, conductive materials are mostly metals. We're generally talking about metals. Well, if I bring this other one and it's neutral, and I bring that over there, I can have charge motion through conduction or charge transfer through conduction. I'm not going to draw them touching, but clearly if I touch them, there would be some charge motion. I'm going to put a wire in between them. That's the same as them touching. Okay, so if I have a wire between them, what would happen? Well, there's a net positive charge. If I think of it this way, I can do two things. First, I can say, okay, well, positive charges attract electrons. If this is neutral, an electron over here would say, oh, I've got a strong incentive to go that direction. So some electron flow is going to go from one to the other. Well, if one electron goes over there, and this is still positively charged, the next electron is also going to go. This is going to keep going, but think of every electron that goes there makes this less positive. I'm going to make it a smaller positive sign. Makes it less positive. So this will keep going. Oh, and this, by the way, as it loses electrons, becomes more positive. So this will keep happening until these charges are roughly equal, if these are similar sized objects. If they're different sized objects, that's different. But in this class, we're going to be talking about similar dimension conductors. So what's going to happen is electrons are going to keep flowing until the charge is balanced. Okay, until this and this are both pulling on electrons equally. So no more electrons want to move over. They're perfectly happy where they are. So if this started out with positive 8 coulombs of charge, and this had 0 coulombs of charge, the total charge will end up being balanced at positive 4, positive 4, because there's conservation of charge. However much charge you had at the beginning in the system, you have to have at the end. So it will keep going until it's balanced. A way of looking at it is this. Suppose that if this was 8 coulombs, positive 8, and this is 0, well, clearly, this is so positively charged, electrons are going to want to move over here. Okay, so it's going to attract electrons. If it attracts 1 coulomb of electrons, that makes this less positive by 1, and this makes this more positive. Oh, there's still an incentive for them to go over there. This is so strongly positively charged. So we could keep playing that game until ultimately we would arrive at an equal number of coulombs, an equal charge on each conductor. Okay, so that's the principle of conduction. You have one charged object and maybe another one that's neutral. When they touch, the charges will move to eliminate the electric field. And that's the other side that I wasn't really talking about. Here, if we look at this, if this started out positively charged, well, the electric field's in this direction. That means there are forces on electrons in that direction. And again, electron moves over, it makes it a little less positive, but it's still, and this makes this a little tiny bit positive. That means there's still a net electric field in this direction. So this continues again until they're equal. So there's two different ways of looking at conduction: through electric field causing charge motion, and through the whole positive attract negative. The bigger the positive, the more the electron's going to be attracted to it. So that's conduction. I'm going to demonstrate some charge motion using this thing called the Van de Graaff generator. Not one of my favorite demonstrations because I always get shocked and it's unpleasant. This Van de Graaff generator has this belt that basically removes electrons from this metal dome. This metal dome has, let's say it's aluminum, it has roughly the same number of protons and electrons right now. It's neutral. And that is because every atom tends to have the same number of electrons as protons. The protons make this aluminum. If we add or subtract electrons, it doesn't really change the material. So the protons stay locked in, right? The way we add a charge or give it a charge is by either adding electrons or removing electrons. We don't add protons. So it's more about what electrons would do. Well, this belt will remove electrons. So let's turn it on. And it's getting a positive charge. Okay, you'll have to take my word for the polarity. The belt's removing electrons. Hate it. And I'm getting shocked because it is so positively charged that it's pulling electrons off of my finger. And I really want you to ignore it. The lightnings kind of look interesting to see. A little more fun if you see it this way. Hurts me less. But what's happening is it's removing electrons from this neutral, formerly neutral dome. Okay? So now that's very positively charged. This is neutral. And if I bring this over, and again, I want you to ignore, oh my God, I'm just getting shocked right and left. I want you to ignore the lightning, the shock that went between them. What I did was I touched that ball to that ball. Now they're both positively charged, okay? And here's why. That was positively charged. When I touched it, it attracted electrons. So it decreased the positive charge on there, increased the positive charge on there as electrons left. And you can see, I'm hoping, and maybe I'll get behind it, you can see these threads. They kind of show the direction of electric field in a way. They're repelling, okay, because everything on there now is positive, and positive repels positive. So that is positively charged. Now what I can do is I can touch that, and it's so positively charged, it'll take some electrons from me. Let me do that. And if I do that carefully, it's going to take a little while for those to fall down. But you can already see they have less charge. If I touch any of these, I'll eventually take away most of the charge of those things because it'll transfer electrons to those threads. Okay, so this was conduction. This was touching and transferring. I'm not a conductor, but some electrons can go from me to these things. And this one's still positively charged, still causing me problems. So that's an indication of conduction in real life. Conductors transferring, touching and transferring electrons between them to balance the charge to some extent. I'm going to speak briefly about conduction and induction. Charging by conduction and charging by induction. Conduction is kind of like what it sounds like. It conducts. So if I have a neutral object, let me just put neutral there, just blank, and a positively charged object, to give this a charge, I can touch them. I'm not going to slide that over. I'm going to connect them with a wire. What happens? Electrons are attracted in that direction. So it leaves behind, electrons flow in this direction, in that direction. It makes it a little less positive. Let me make it just a smaller positive. And it makes this a little more positive because electrons have left. And they will end up, if they're equal sizes, with equal charges. But it doesn't matter. If this was positively charged, even if they're different dimensions, and this was neutral, after some electrons leave, this will be positively charged, this will be slightly less positively charged than it was. So that's conduction. It's pretty logical. We've talked about that. Induction is another way of charging an object, okay? And it's like this. Here's a neutral object. And I'm going to bring a positive charge close. Now, what's going to happen is, yes, electrons are going to tend to move to that side, but it's still going to be neutral. If I took it away, this would redistribute and be neutral. So make it polarized as it comes close, separate some things out, and then as I pull it away, go back to normal. I'm not going to touch it, but what I can do is I can attach a wire to ground. And remember, ground is an infinite source or sink, an infinite supply of electrons or an infinite destination for electrons. So when I hook that up, what happens? Well, electrons want to go that way. So electrons will flow from Earth, from ground, in that direction. So this will get electrons coming this way and more and more and more and more and more, depending on, until the electric field is essentially neutralized. What do I mean by that? Well, if I only have one excess electron here, and I have a positive charge there, the electric field from this is in this direction. The electric field from this is in that direction. It's in that direction. So electrons are going to, as I add more and more electrons here, fewer are going to want to come. So eventually you've got so many over here that the next electron isn't going to want to come. And so when I've got a big negative charge here, at some point the electrons stop flowing. Okay, they're pretty happy. There are a whole lot more electrons there, and a whole lot more protons, but this field made some of them come up here. Now, if I break that connection, disconnect from ground, and I take this away, this is a net negative charge. Those electrons will redistribute, but it will have a net negative charge. And that's induction. Okay? Similarly, I could have brought a negatively charged object close. So here's a neutral object. I bring a strong negative charge. And if I connect it to ground, electrons are going to want to move in that direction. Right? The electric field is in that direction. Electrons move the other direction. So I have unmatched protons in here. And if I then break this, the electrons can't come back, and I take this away, then I end up with a randomly distributed net positive charge. So conduction, they can move directly from one object to the other. The charges can move directly from one object to the other. If they're equal sizes, it will balance out. Induction is I create a field on that thing, and then I connect it to ground and let charges flow on or off. And then when I separate them again, when I isolate that thing, it's now got a charge. It's charged by induction or charged by conduction.